Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.1. Areas and Riemann Sums.
Lesson 2. Definition of area and Riemann sums. Part 2. Let's return to our example y equals root x and just see why we might want to choose arbitrary x values or intermediate x values rather than choosing the left-hand endpoint or the right-hand endpoint on each subinterval. And I'm going back to our y equals root x, where I could write f of x equals root x function that we started out with in this section. I'm going from 0 to 8 and trying to approximate that exact green area that we had under the curve from 0 to 8. Well, before what we did was we used either the right-hand endpoint to create each of our rectangles or the left-hand endpoint to create each of our rectangles. And now what I'm going to do is choose another point on each strip, and in particular I'm going to direct us to choose the midpoint of each subinterval to calculate the height of the rectangle. So what do I mean by that? Well, let's look at this first strip that goes from 0 to 1. Instead of choosing 0, the left-hand endpoint, to create the height of my rectangle, or 1, the right-hand endpoint, I'm going to choose the midpoint. And halfway between 0 and 1 would be 0.5, or 0.5. So that is my x1 star value. And when I go to my second strip, again, I'm going to use the midpoint of that. So instead of using 1 or 2, I'm going to use 1.5 halfway in between those, and that would be my x2 star, and so on. Let's see what the others would be. Between 2 and 3 I would use 2.5, between 3 and 4 I would use 3.5, and so on. On the very last rectangle, the 8th rectangle, instead of using 7, the left-hand endpoint, or 8, the right-hand endpoint, I'm again going to use the midpoint, so that would be 7.5, and this would be my x sub 8 star. It's my arbitrary, although I've dictated exactly which point we're going to use. It's my x value, arbitrary x value between 7 and 8. So what happens now? On this first strip, I'm going to use 0.5 as the place where I figure out the height underneath my curve. So this red line here is how high I'm going to make my rectangle, and it's going to stretch from the left-hand side of the strip to the right-hand side. And so my first rectangle would look something like this. And on my second strip, here's the height that I'm going to use, that red height, but the rectangle is going to stretch from the left-hand side of this strip to the right-hand side. So here's my second rectangle. And I do this on each of these strips. I choose the midpoint to create the heights of my rectangles, and I'll just kind of quickly draw in those red heights. And then just make sure when you draw your rectangle that it has this red height but stretches from the left to the right side of that original strip that we had that's bounded in green. So my rectangles will look something like this. I'm trying to make the tops horizontal. And so I'll just kind of shade those in. So this is what my approximation looks like, just so we can kind of compare it in our minds with what we had for the left-hand heights and the right-hand heights for this example. And let's go ahead and see if we can figure out what each of those heights are so that we can write out the sum. This I'm going to call m sub 8 because we are using the midpoints rather than r sub 8. We use the right hand endpoint of each subinterval, and L sub 8 we use the left hand endpoint. Here we're using the midpoint, so we usually say m sub 8. So if I want to know what the area of that first approximating rectangle is, I have to do its height times its width. Well, what is its height? Its height is this red height right here, and that's going to be f evaluated at that arbitrary x value that I chose, or in this case it was prescribed for me, the midpoint value. So it's going to be f evaluated at 0.5 or 0.5. So the height of that first rectangle is f evaluated at 0.5, but my function is given to me in this case, it's the square root of x, so the height will be square root of 0.5. I multiply by the width. The widths are still 1 unit because my rectangle stretches from 0 to 1, 1 to 2, and so on. So the widths of these rectangles are the same as when we were doing L sub 8 and R sub 8. The widths of the rectangles are still 1. So that would be the area of my first rectangle, square root of 0.5 times the width, which is 1. Now I go to my second rectangle. Well, what's the height of that? It's just going to be my function evaluated at 1.5. And then it's going to be times its width, which is still a width of 1. So what is f of 1.5? Well, for this function, it would be the square root of 1.5, and I multiply that times 1. The third rectangle would be square root of, well, the midpoint of the third strip is 2.5, and the width is still 1, and so on. And we would go all the way up to the last rectangle here, which has a height that would be evaluated at 7.5. So the height of this last rectangle is f of 7.5. And for this function, f of x is root x, so that would be square root of 7.5. And I multiply by its width, which is 1. So let's go ahead and see what exactly that comes out to be. I plugged all of this into a calculator and got approximately 15.13847 roughly. So this m sub 8, the exact area, if you remember we talked about that before, is 15.08494. This m sub 8 is off by about, I'll say off by, not very much. Let's see. It looks like it's off in the hundredths, the tenths and the hundredths decimal place, but not by very much. It's only off by about 0.05. So that's actually pretty good. If you remember, when we did R sub 8 and used the right-hand endpoints and L sub 8 and used the left-hand endpoints, these were off from the true area by more than a whole unit. And here we're off by only around 5/100ths of a unit. So this m sub 8 is actually a huge improvement in what's called the efficiency of our approximation. We think of something as being more efficient if it has the same number of calculations but gives us a much closer result. And in general, for most curves, the midpoint rule will give you a much better estimate for the area under the curve than either the left-hand rule or the right-hand rule would. And why is that true? If you notice, at least for this function, it's very prominent because the function is always increasing on the interval from 0 to 8. And the left-hand rule we said was always going to be too small of a rectangle. The right-hand rule was always going to be too large. And when we choose the midpoint on an increasing function like this, it's something that's in between, intermediate in height. And so it sort of cancels out. You notice like on this little strip right here, you can see the white part is an error. That's where it's too small, and the part that it hangs over, this purple part above the curve, is an error, but those two kind of cancel each other out on that strip, and so the purple rectangle of intermediate height does a much better job of approximating the true area under the black curve. And you can even see it if we go back to that overhead that we had for the left-hand rule and the right-hand rule. If you look at the total amount of error, either stuff over this curve or under this curve for the midpoint rule, you can see that those sort of cancel each other out all the way along, and it does look like these purple rectangles will be much closer to the true area than when we used the right-hand rule with 8 rectangles, or when we used the left-hand rule with 8 rectangles. And that does turn out to be true. So let me just place that here for a moment. Here was the right-hand rule. You can see there's a lot of stuff that's over, and every rectangle overestimates the area of the true strip. And here's the left-hand rectangles, and they're all under the curve. Now, if the curve were partly increasing and partly decreasing, then the midpoint rule might not be a lot better approximation for the area under the curve. It may not even be a better approximation for the area under a particular curve on a particular interval. But in general, it will do a better job because the errors, the amount that rectangles are over and under, tend to cancel each other out. And here, just kind of for your information, I did M sub 16, I did M sub 32, M sub 64, and M sub 1024. Well, what are those? That's just the midpoint rule with 16 rectangles, 32 rectangles, 64 rectangles, and 1024 rectangles. And when you get out to 1024 rectangles, we are good actually out to this decimal place. What is that? Tenths, hundredths, thousandths. It's good out to the 10,000th decimal place. So that is looking really, really close. And this you can check with the average that we did of L sub 124 and R sub 1024. When we divided that by 2, I think we got a value of, so that was the average of those two. This turned out to be a value of 15.0848198. And so this is really good only until we get to the thousandths column rather than the 10,000ths column as in this one. So this M sub 1024 is even better than the average of L 1024 and R sub 1024. So the midpoint rule is a rule that we use quite often. It's more efficient in general because it usually gives you a better approximation for the same number of calculations. So it takes you essentially the same amount of time to do the calculations, but gives you a much more accurate estimate for the true area under the curve. Well, now what I'd like us to talk about next is the most general form of a Riemann sum. You might remember that I said that in the general case, L sub n, where you use the left-hand endpoint to create the heights of your rectangles, and R sub n, where you use the right-hand endpoint, or even when you use an intermediate x I star value on each subinterval, that these were special cases or examples of a more general sum called a Riemann sum. So these are examples or special cases of a general Riemann sum. And let's go ahead and just talk kind of briefly about that general Riemann sum. So what we are doing here is we are kind of generalizing a little bit more, loosening a little bit more the conditions on those rectangles. Remember, originally we said we had to use the right-hand endpoint. Then we said, okay, well, could we also use the left-hand endpoint? And then we looked at what happens if you use an intermediate value. If you remember back a couple of pages, We talked about what happens if you use an arbitrary x value in between the endpoint values to create the heights of your rectangles. And we said that also gives you an approximation for the area under the curve. Well, let's loosen our conditions a little bit more. And we're going to ask this question: what if not only do I allow us to use any x star value on each strip, so I can use any intermediate x value that I want to create the height of my rectangle, what if I also allow the widths of the rectangles to be different, to vary? Remember, we said that we divide this up into n equally spaced strips, but now what we're going to do is say, well, do the strips really have to all have the same width? In other words, when I create these rectangles, does the distance from, say, x0 to x1, does that really have to be the same as the width of the next rectangle from x1 to x2? So what we're going to do now is loosen our conditions a little bit more and see if we still get an approximation for the area under the curve. So in this picture, you notice going from x0 to x1, I have a rectangle that has a certain width, but the next rectangle looks skinnier, and the next one looks skinnier still. So what we're going to do is say, well, I can't call them all delta x anymore because the widths are not all the same. So I'm going to call the width of the first rectangle delta x sub 1. And I'll call the width of the second rectangle, that would go from x1 to x2, I'll call that delta x sub 2. And the width of the third rectangle, well, that looks really skinny. That's kind of hard for me to even draw on there. That would be delta x sub 3, and so on. So now I'm allowing the widths of the rectangles to vary, to be different from each other. If I go to the very last rectangle, it's the rectangle that goes from x sub n minus 1 up to x sub n, and so its width would be delta x n. It's just the width of the nth rectangle. Well, if I go ahead and create these rectangles, does it look like when I add up the areas of these rectangles, and I kind of drew the rectangles in for us because it takes a while to do that, does it look like that will still give me an approximation for the area under the curve? And it does. When I add up these n rectangles, it does look like they'll be roughly equal to the true area under the curve, y equal f of x from a to b. Well, let's go ahead and see if we can write down what the areas of those rectangles are. So let's start with the first rectangle right here, and let's go ahead and just kind of shade that in so we can see what we're doing. I'll try not to go over my center line there. If I want the area of this first approximating rectangle, as usual, I need its height times its width. So let's see if we can figure out what that is. Well, the height of that rectangle is this red dotted line. I've chosen an intermediate x value, an arbitrary x value between x0 and x1 to create the height of my rectangle. Well, how high is that? It's going to be f evaluated at this x value, so it'll be f evaluated at x1 star. So the height of my first rectangle is f of x1 star. Just like in our general picture that we had 2 pages ago, where we chose an intermediate x1 star value, and the height of our first rectangle was f of x1 star. The only thing that's different is that now the width of my rectangle is not delta x, it's delta x1. So the width of my rectangle could be different than the widths of the following rectangles, the ones that come after it, so we call that delta x sub 1. It's just the width of the first rectangle. And we keep doing this. Let's go ahead and go to the second rectangle. If I want to figure out its height, well, I'm evaluating the height at x2 star, so it would be f of x2 star. And so the height of the second rectangle is f evaluated at x2 star, and its width is a different width. It is a width of delta x2. So the only thing that really changes from what we did a couple pages ago, where we found a sum and we used an arbitrary x star value within each subinterval, the only thing that really changes here is that we're allowing these widths to be different. The width of the first rectangle is delta x1, while the width of the second rectangle is delta x2, and so on. And let me put some dots in there and we'll go to the last rectangle. For the very last rectangle, that's this one right here. Let's see if I can shade it in for us just so we can see exactly where the sides of that rectangle extend to. So this is the last rectangle. And if I want to know what's the height of that last rectangle, well, it's just going to be f evaluated at xn star. So the height will be f evaluated at xn star. That's my arbitrary x value on the nth strip. And then I multiply by its width, which we said is delta xn. X sub n. And so the only thing that's really changed is that we are now also allowing each of the widths to possibly be different from each other. And when we do that, we get the most general form for a Riemann sum. All the other ones that we talked about, the L sub n, the R sub n, if I do the midpoint rule, all of these are special cases of this general sum where the arbitrary x value that you chose might have always been the right-hand endpoint. And the delta x1, delta x2 through delta xn that you chose, the widths that you chose, happen to all be equal to each other. So these were all examples of Riemann sums. They were special cases of Riemann sums, but this is the most general Riemann sum. We can see that it still creates an approximation for the area under the curve, the exact area under the curve from A to B. But there is an important question down here. As we let the number of rectangles n go to infinity, will this approximation get closer and closer to the true area under F, the way it did for L sub n, for R sub n, and for the midpoint rule? Well, the answer to that is a little bit complicated. I could answer it with maybe. And let me show you what the problem might be. I'll put in parentheses, it depends on how we let the rectangles go to infinity. Maybe that's sort of a rough way of saying it. So let's go to the next page and I'll show you the problem that could come up with simply saying, well, yeah, we're going to let the widths all be different now, and I'm just going to start increasing and increasing the number of rectangles, and when the number of rectangles goes to infinity, boom, I've got the exact area under the curve. Well, there is a problem. It depends on how somebody devises their scheme for increasing the number of rectangles. So let me show you the problem that might occur. We're allowed to have our rectangles have any width that we want to. So here's y equal f of x, and what I've chosen to do, since I have all this freedom now, is I've chosen to sort of split this interval between a and b in half right at this point. And what I'm going to do is say that the last rectangle has to be half of this interval's width. So here's my delta xn. That's my last approximating rectangle. And I'm going to make all my other rectangles have an equal width. So think of these maybe as all having an equal width. And I'm going to start subdividing more and more. I'm going to allow my number of rectangles to go to infinity, but I'm going to do it in such a way that the last rectangle always has this big fat width. So this stays as a big fat rectangle, whereas these are all going to start subdividing more and more and get skinnier and skinnier. So these get skinnier and skinnier. And the question is, if I let the number of rectangles go to infinity by just making more and more over here and leaving this one alone, even though n is going to infinity, does this get closer and closer to the true area under this curve from A all the way up to B? And I think you can see that since this last rectangle is fixed as this big fat thing that clearly is not exactly equal to the area under the curve from this midpoint up to B, that even though these will get closer and closer to the area under the curve from A up to this midpoint, and eventually as n goes to infinity will be the exact area under that curve, this one will not. It'll always be off. There'll always be an error here. And so even though we're allowing the number of rectangles to go to infinity, we haven't done it in a way that will end up giving us the exact area under the curve. Well, what's wrong with the scheme that I had here? Well, the problem with this scheme is that even though the number of rectangles is going to infinity and we get more and more rectangles, the widths are not all getting skinnier and skinnier. Only these were getting skinnier and skinnier. We need all of our widths of our rectangles, including this one, to eventually get smaller and smaller and smaller. So we have to devise a scheme in which the number of rectangles goes to infinity, yeah, but also all of the rectangles eventually shrink to being something that's thinner and thinner, infinitesimally thin. In other words, a tinier and tinier width. So let's go ahead and say that we must insist that all of the widths, the delta xi, where I've left I as some unknown width, one of these widths, but all of the delta xi must eventually go towards, well, we said they have to get smaller and smaller, and in particular they have to get closer and closer to 0. So all of my rectangles must eventually get infinitely thin. The widths have to go to 0. And we do this by specifying the following. We specify that the maximum of all of these different widths, so with every partition, every subdivision of A to B that we create, we make sure that the maximum width, as the number of rectangles gets larger and larger, eventually goes to 0. If we specify that the maximum width of all of these rectangles goes to 0, then all of the smaller ones must also be going towards 0. So we write it this way. We write max, meaning the maximum of all the delta xi's as I runs from 0 up to n. Those are just the different widths of our rectangles. And we insist that the biggest of those goes towards 0 as the number of our rectangles increases. If the maximum width goes to 0, then all of the smaller widths must also eventually go to 0. So instead of saying that the area is simply the limit as the number of rectangles goes to infinity of this Riemann sum that we talked about, the f of x1 star times delta x1 plus f of x2 star times delta x2 and so on up to f of xn star times delta xn. We said we can't really just say let n go to infinity. We might get ourselves into a situation like this, and the exact area will not necessarily be equal to this. So this does not work. It really would depend on how the number of rectangles goes to infinity. To make sure that we do end up getting the exact area under the curve all the way from A to B, we have to write the following, and we write it this way. The limit, and instead of saying the number of rectangles goes to infinity, we just make this statement right here. The maximum of all of the widths, and I leave this as an unknown subscript, so the maximum of the delta xi, where I could be any of the widths from I equals 1 up to I equals n, the maximum of those has to go to 0. So we say the exact area would be the limit as the widths go to 0 rather than as the number of rectangles goes to infinity. And then we just put the same Riemann sum in there. So we'd say f of x1 star times delta x1 and so on all the way up to f of xn star times delta xn. And by saying that the maximum of all the widths goes to 0, it means that the widths of every one of our n rectangles, delta x1, the delta x2 that I haven't written here, up through delta xn, all of those eventually shrink down to 0. And so our rectangles get thinner and thinner and thinner, and eventually we'll get the exact area under the curve. Well, this idea of the more general Riemann sum that we talked about is a little bit more abstract because we've really loosened up our conditions, not using always the left-hand endpoints or always the right-hand endpoints or even always the midpoints or even an arbitrary point, but also adding on this idea that the widths themselves, the delta xi, could be different. So it's a more general way of estimating the area underneath the curve, and then this idea that the maximum of all the widths has to end up going to 0. It's a bit more abstract than what we talked about with the Ln and the Rn and the Mn. So you might want to re-listen to that part of the tape, the last page and this page again, or read about it in your textbook, and it will give you even more detail in your textbook to really understand this idea. In practical terms, we rarely use the Riemann, the most general form of the Riemann sum. We're usually using left-hand endpoints or right-hand endpoints or midpoints to estimate the area under the curve, and most of the time we are using intervals that are all the same width. And you might wonder, well, why would I ever want to use widths that are not all equal? It's so much easier to take this interval from A to B and divide it up into n equal subintervals instead of ones that have different widths to them. And let me just give you at least a partial answer to that question. So if you turn to the next page, it has that question at the top. Why would we ever choose different widths? It seems difficult. Here was our picture with R8, where I'm using the right-hand endpoint on each subinterval, and you notice that all of the widths are the same. So this is the picture with equal widths. And this orange part here, or red, I'm not sure what color that is, this is the error. So these things here, these orange parts, are the error. It's how much our rectangle estimate of the area under the curve is off. That's how much each of these rectangles is hanging over. So this red part here is the error, and this is what it would look like with equal widths. Well, it turns out that if you have a function like this, at least for one that is always increasing on the interval you're concerned with, 0 to 8 in this case, the parts of the curve that are rising more quickly, that are steeper, so the slopes of the tangent lines would be steeper at this end of the curve, and here you notice the curve is kind of flattening out. The slopes of the tangent lines would be smaller slopes, they would be shallower. It turns out that it pays off to use more rectangles where the curve is increasing more steeply. So you notice that I'm still using 8 rectangles here, but they now have unequal widths instead of equal widths, and I've bunched up the rectangles near this portion of the curve where it's rising very quickly. It has steep tangent line slopes. And it turns out that if you add up the error in this case, for the picture that I have, the error is less for these 8 rectangles, so the sum of all these little red errors here would be less than the sum of all the little red errors when we used equal rectangles. So this is a case where we would say using unequal widths is more efficient. And remember, we talked about the word efficient before. Efficient just means that you're doing the same number of calculations. This is still 8 rectangles, so we have to do exactly the same number of calculations that we did up here with our equal widths, but we get an estimate that's closer to the true area. We get a better result. So that's what we mean by more efficient. Same number of calculations, but a closer estimate to the true area under the curve. Well, there's a mathematician who taught at UC Berkeley back in my day. Don't know if he's there anymore, probably not. And that was one of the things that he worked on, was figuring out what's the most efficient system for a general curve, what's the best way to choose the widths of these rectangles so that you still are using the same number of rectangles but get a better approximation.